Hello everyone, today our team would like to present our project titled Deep Learning Based Helmet Non-Compliant Detection in Construction Site Safety Monitoring. This project focuses on applying deep learning techniques to automatically detect helmet violation in construction environments, with an emphasis on real-time performance and practical deployment. Now, let me begin by introducing the motivation behind this work. To give you a clearer picture, our work today presentation is divided into five main sections. First, we will start with the introduction to understand the necessity of this project. Second, we will look at the datasets and how we prepare the image. Third, I will explain the training process and the technical improvements of YOLO V8. The next part will analyze the result and some real-world detection case. Finally, we will wrap up the conclusion and our plans for future development. Now, let's move to the first paragraph, introduction. Construction sites are inherently high-risk environment where strict safety compliance is essential. Although regulation clearly require workers to wear helmets, violations still occur. Moreover, traditional manual monitoring is inefficient, labor-intensive, and prone to human error. Therefore, our objective is to develop an AI-based vision system that can automatically detect helmet compliance and violation in real time. Regarding our detection target, the system focuses on three core classes: person, helmet, and no helmet, which are essential for identifying safety violation. To provide a more comprehensive safety monitoring solution, we have also expanded our model to detect vest and no vest compliance. This expansion allows the system to not only monitor head protection but also ensure that workers are wearing high visibility clothing on site. Next, in the dataset, for training and evaluation, we use the construction safety dataset from RoboFlow. Its content approximately 1, 1000, 1010, 1200 annotated image on resize to 640 by 640 pixels to match the input requirements of the model. The dataset was divided into training, validation, and test sets to ensure reliable performance evaluation. Importantly, the image include variation in position, scale, and background complexity, which helps the model generalize better in real-world conditions. Having introduced the dataset, I will now hand over to my teammate to explain the model and training process in more detail.
For this project, we selected YOLO V8 as our primary detection model. YOLO V8 adopts an anchor-free architecture and a decoupled detection head, which improve localization, accuracy, and training stability. To ensure optimal conversion, we implemented a progressive training strategy consisting of three steps: 20, 50, and one, 100 epoch. This approach allows the model to gradually refine feature representation while minimizing the risk of overfitting. Now let's examine the training result. After 100 epoch, the model achieves an overall MAP at 0.5 of approximately 86.7%. More specifically, helmet detection reached 95.4%. No helmet detection at least 70%. The training and validation loss curve decreased steadily without significant diversion, indicating stable conversion behavior. And additionally, the confusion metric showed low misclassification among safety-related classes. However, selecting a model is not only about accuracy, it's also about confidence, calibration, and deployment readiness. To determine the optimal deployment threshold, we analyze the F1 confidence curve. The observe that the F1 peak shift from 0.206 in early training to 0.325 after full conversion. This shift indicates that the model becomes more confident as training progresses. Based on this analysis, we select a confidence threshold of 0.4 for deployment. This value effectively reduce false alarm while maintaining high recall, which is critical in safety monitoring system. In addition to YOLO V8, we also conduct a comparative evaluation with YOLO V5. This is a result of YOLO V5 model. I have compiled some parameters for comparison between the two models. From the table, YOLO, we can see that YOLO V5 a 3-year higher overall MAPs. However, YOLO V8 performed better in helmet detection and also shows stronger vest detection and improved person classification stability. Although YOLO V5 achieved higher performance on the no helmet class, YOLO V8 provides better helmet accuracy, better vest detection, improved person classification stability, higher recall, and more balanced multi-class performance. Therefore, considering stability and real-time deployment required, YOLO V8 was selected as the final model.
With the model and evaluation complete, I will now presenting the real-time implementation and system performance. For real-time development, we integrated the trained YOLO V8 model into a local environment using OpenCV for webcam input processing. To improve practical reliability, we implement an additional geometric validation mechanism. Specifically, the system checks whether the detected hit regions lie within the bounding box of a detected person. This significantly reduces false detection caused by circular background objects. Furthermore, we apply multi-threading to separate the alarm function from the image processing pipeline. As a result, the system maintains a stable frame rate of approximately 25 to 30 bps, even when triggering warning sound. Now, let's look at the detection result. The example so here illustrates both successful detection and challenging case. In most scenarios, the system accurately identifies helmet compliance and violation. However, under difficult lighting conditions or partial occlusion, some violation may be missed. This result demonstrates both the effectiveness of your approach and the limitation that guide future improvements. In conclusion, we successfully developed a deep learning-based helmet violation detection system suitable for a real-time construction site monitoring. The model achieved high detection accuracy, stable coordinate, and reliable real-time performance. By combining scientific parameter selection, comparative models analysis, and intelligent processing logic, the system demonstrates strong practically feasibility. In future work, we aim to expand the dataset, improve detection under challenging conditions, and integrate hardware-based alert mechanisms. Thank you very much for your attention.